Homework 13, measures of average video 2, mean for ungrouped data. I have to assume most, if not all of you, know how to find the average of a set of numbers. So when I introduce the notation, don't let it throw you off. It's just saying find the average. Let's let the set containing x1, x2, and a bunch of values that we don't know how many there are, so we'll generically call the last one xn. So that n is how many values we have. But let x1, x2, all the way through some last number xn be a set of quantitative data. So they're numbers. The mean, denoted by this symbol, an x with the bar over it. And by the way, this symbol, which is the variable for mean, is read x bar. So anytime you see that, you just read it x bar, but it means the average of the mean. The mean, denoted by x bar, is x bar equals, now here's what you already know, you add up all of your x's, or all of your values, and after you've added them up, you divide by how many values there are. Now there is a more compact way to write this formula without the need for the ellipses here to indicate all the missing values that we're not representing explicitly. And I'm showing you this because if you click view an example or guided solution, it's going to bring up this notation, and I don't want it to worry you. There is a way to represent the sum of a bunch of expressions when the only thing that's changing is a certain piece of them. In this case, the thing that's changing are the subscripts, 1, 2, all the way to some unknown last number. One way to write this more compactly is to use a capital Greek letter sigma, which looks like that, and write one of these terms with a generic subscript. Now I can't use n because that already has a meaning in this context. It means how many numbers we're adding. So the default generic subscript here is usually I. But all this means on the top of this is the sum of all the x's, which are representing the values in our set. So it's just a compact way of saying add all of these. Instead of explicitly listing out all of them, well, not all of them because we have the ellipses here, find the sum of all these values and then divide by how many you had. So when you see that, don't panic. It just means add all the numbers. So for example, let's find the mean of this very small data set. Now we're going to do a follow-up to this, so if you've already calculated the mean, in fact I invite you to pause the video and calculate the mean, but afterwards I'm going to throw one more number in there to make a point. To find the mean, all we have to do is find the sum of all the values, so 5 plus 9 plus 10 plus 11 plus 17, and then after we find the sum divided by the number of values, there are 5 values in this data set. So let's see what the sum is. Let's see if I can do this efficiently. This 9 plus this 11 makes 20, plus 10 makes 30, plus 17 makes 47, and plus 5 more makes 52. So the sum of the values is 52, but now to find the mean, I have to divide by 5, and that's going to be 10.4. So it's just the average, folks, or what you commonly know as the average. I should clarify that the word average can actually mean a variety of things. You commonly know it as add and divide, but technically that move is called the mean, and more specifically the arithmetic mean, but let's not go that deep. So what did I want to do to illustrate something? Well, averaging is okay, or rather I should say finding the mean is okay, but there's one flaw with calculating the mean. And I'm going to illustrate that flaw by posing the same question, find the mean, the same numbers, 5, 9, 10, 11, 17, except I'm going to add one more number. I'm going to add what in statistics is called an outlier. An outlier, loosely speaking, is a number that is noticeably larger or noticeably smaller than the other numbers in the data set. In statistics, you get a more rigid definition on what qualifies something as an outlier, but for now, let's just say something that's way bigger than the other numbers or way smaller than the other numbers. So for example, let's say for an outlier, over here I put 5,000. Obviously, noticeably larger than the other values. What do you think this will do to the mean? Previously the mean was 10.4. Do you think it's going to be close to that? Probably not. Because when you have an outlier, it can drastically change the value of the mean. Now we already know that the first 5 numbers add up to 52, so I'm not going to write all those again. But now we pick up the 6th number. So here's the sum of the first 5 plus the 6th, and now we have 6 numbers, so we divide by 6. So this is 5,052 divided by 6, which is a lot larger than 10. Let's see what it equals. 5,052 divided by 6 is exactly 842, which is a lot larger than the mean without the outlier. So what point am I making here? The point I'm making is the mean is heavily influenced by outliers. And for that reason, sometimes it's not a good measurement of average, because it might not accurately represent a data set very well. The mean of this data set is 842. Never mind the fact that most of them are way less than that, it's the mean. Up here, not such a big deal. The mean was 10.4, some are less, some are more, but none of them stray too far away. Here's another way of thinking about the effect of an outlier on a mean. Let's say that you're sailing pretty smoothly in a class. You make A's on the first couple of tests, even the first 3 or 4. And then suddenly you make a 30. That outlier severely drags down your average. So it works in both directions. A really large outlier can severely increase the mean, and a really small outlier can decrease the mean. But the discussion about outliers and the effect that they have on the mean is really kind of foreshadowing what you will see in a statistics class. For your purposes, as long as you can calculate the mean, which you commonly know as the average, you're going to be fine.